Well, good afternoon. It's now 2:33, 3 minutes late getting started for differential equations. I waited as long as I felt like I should to wait to see if a student would come in, but so far none, so I'll go on and get started from where we left off last time. When anybody comes in, then I'll go over a couple of announcements, but until then, let's just hit differential equations. We're still in chapter 1. It's a pretty long, it's a short chapter, but it has so much a variety of things in it that it's sort of hard to rush through. So we're sort of slugging through here in chapter 1 and section 1.1, definitions and terminology. So my memory is we're on page 6, near the top of the page. We just had talked about the third classification of differential equations. The first was the type of differential equation, either ordinary or partial. We're dealing only with ordinary. Then we classified according to order, and that was what is the maximum derivative represented in a differential equation, okay? And you could have a variety of those. And the third classification is classification by linearity, and that's given a derivative, in whichever order of derivative you have, as long as those orders of derivatives are not raised to powers, whether they be positive powers, negative power, fractional power, or anything, it can only have exponent of 1. And the y values can only have exponent of 1. The x can be anything it wants to be. Then that designates a linear differential equation. And we finally got a student here. Good. Easton's here. Okay. And with that, I will turn on the projector. And we can turn on the light for you. Now that really needed, but just in case it makes reading stuff a little easier, but if it makes it worse, we'll turn it off. And let me go over a couple of announcements. Did you hear about the college transfer days? Okay, so that we've been over. And the summer research program at 3 universities, University of Illinois, Arkansas, and Howard. Have you heard about that? Okay. What this is, written by probably a Dr. Joseph Muskin. And he runs the summer research program for the Center for Power Optimization of Electrothermal Systems. It's POETS, Power Optimization of Electrothermal Systems. We're looking to recruit minority engineering students to work at 3 of the 4 institutions this summer, University of Illinois, University of Arkansas, and Howard University. It's a 10-week internship program that exposes undergraduate students to academic research in the fields of mechanical, electrical, and material engineering. Okay, so it's an incredibly great learning experience. And guess what they do? They pay you to have it. They pay you $5,000 stipend to attend and participate. That's $500 a week, okay, just to go. Now, not just that, they provide free housing for you, okay? And usually the housing includes meal card. So free food for 10 weeks, okay? And they fly you there and back once, one round trip flight. To get you there and get you home. You come home anytime in between, that's on you, okay? One round trip. And you gain access to weekly professional development webinars, as well as other benefits, and I have a brochure that I'll show you. The deadline for application is February 15th, and there's other information in here, websites, emails, a variety of things like that, and a brochure. And the brochure I printed on scratch paper, one side, the other side is fine. I can hardly read this one. It's light blue with white print on it, and it's really hard to read. But the inside part is readable. So if you're interested, you certainly are welcome to take pictures of this or do whatever you want to with it if you want to participate. All right. Now, any questions on anything before we begin today? I already sort of got started. I was just reviewing the classifications of differential equations we've done. Order, that's either ordinary or partial. We're only doing ordinary. Order, which would be what the maximum derivative involved in any of those differential equations. And then the last one we started last time was linearity. It's linear if all your derivatives and all your y's are only to the first power. You don't have any crosses or other things. Those are linear. If they're not, then it's nonlinear. So here is example 4, and it gives you some equations. Okay, let me get my pen set up for example 4. Here's an equation. Y minus x dx plus 4x dy is equal to 0. Okay? Now that's not quite what I would consider a standard representation of a differential equation, though in many respects it is exactly a differential equation, but it's not how we're used to seeing them. Can you tell whether that's linear or nonlinear? What's that?
I said it's kind of hard to tell.
I can't.
I said it's kind of difficult.
Yeah, especially in this form. Okay? Now, what you can do is write it in the form that we're more used to seeing. And that would be get your dy over dx written as a derivative. So you do that by dividing everything by dx. Now, technically, that's not what you're doing, but that's really what it seems like. Here, the dx's go out. Here, this stays 0, okay? So what do we have now? I'm going to rearrange the order a little bit. 4x dy dx plus y minus x is equal to 0. Now, if you don't like having that x in there with the y, you can add that to both sides. And then you have 4x dy dx plus y is equal to x. Is that any easier to see? That would be linear, because this is only to the first power, this is to the first power. It doesn't matter about the coefficient function of x, as long as there's no y's in it. This one, as long as that y is to the first power, is only to the first power, no fractional powers, no higher powers, no decimal powers, no negative powers. It's just power of 1, and over here, any function of x will do. Okay? So that is a linear first order ordinary differential equation. Okay? Here's another one. Y double prime minus 2y plus y is equal to 0. Now I have a feeling there's something a little bizarre about that, but it's okay. There's nothing wrong with it. What about that? Is that linear or nonlinear? It is linear. Now, written the way it is, that would be the same as y double prime minus y plus 0 is equal to 0, which would certainly be linear. I have a feeling that was supposed to have been minus 2y prime. Now, they didn't have that in the book, but I think that's what they did. That would still be linear, because none of your derivatives and none of your y's are multiplied by anything except the 1, the number 1 or 2. I mean, no squares in any derivative, no squares in the or any higher power or anything else. So that is linear. Okay, and here's, by the way, that's ordinary, second order, linear. Okay, here's another one. X cubed, the third derivative of y with respect to x cubed plus x dy dx minus 5y is equal to e to the x. Question, is that linear or nonlinear? It is linear, okay, because your third derivative doesn't have any other y or a derivative of y multiplied by it. Your first derivative doesn't have any y or other derivative of y multiplied. Your y doesn't have any other y or derivative of y multiplied by it. And it doesn't matter what that function of x is at the end, e to the x, that could be anything. That doesn't have to be linear. It isn't, but it doesn't need to be. The coefficient functions are all functions only of x, no y's in them either. This is a function of linear, and that is a function of x alone. So, those three were all. Now, taking a look at it, that's an ordinary differential equation. Third order differential equation, because it has a third derivative in it. So the first one was the first order, second order, third order. All three linear, though. Okay. Yeah. Now, the B part of this example 4 would be this one. Here's an equation. 1 minus y prime, plus 2y is equal to e to the x. Is that linear or nonlinear? It is nonlinear, and here's why. Because this one doesn't bother anything, but here's a y times a y prime that's nonlinear. Because you have a function of y multiplied by a derivative of y, nonlinear. This y is perfectly fine, no sweat there. And it doesn't matter what the function of x is on the other side of it, perfectly okay. But this is what makes it nonlinear. Now, if you try your best to eliminate that, you would have to, at some point, divide by either 1 minus y or y, and then when you did that, you wind up with y in the denominator, which is not an exponent of 1, something to the minus 1. So that is definitely nonlinear. First order, ordinary, but nonlinear. Okay?
I think it makes more sense to me when I think of it in like the line use notation.
Right.
Because like when you multiply,
Right. This is one.
yeah, when you multiply that, another function is, that's basically an operator. So like, when you multiply it by the y, it becomes the derivative of y squared.
Well, not quite, but you got the general idea. The y's are not all at the first power, because that's a y and this is a derivative of y, so the product of those is no longer y to the first power. or y prime to the first power. Neither. So, yeah, that's it. That product is what messes it up. Except the fact that Mensa came in and that clears it right back up again. Okay. All right. Now, we're doing example 4, top of page 6 in chapter 1, introduction to the differential equation 1.1, definitions and terminology. Now, the B part of example 4 is this one. d2y dx squared plus sine y is equal to 0. The question here, is that a linear or nonlinear differential equation in the variable y? Nonlinear. Well, this is perfectly fine. That's just not raised to any power, but this is not a linear function of y. That's a sine function of y, which is definitely not linear. So yeah, if that had just been plus y, linear. Okay? So sine y, not. Okay. Second order, ordinary differential equation, but nonlinear. Let's see if we can squeeze one more in here. D to the fourth y dx to the fourth plus y squared is equal to 0. Linear or nonlinear? This one. Nonlinear. This is perfectly fine. Again, it's a higher order derivative, but fine. Fourth order differential equation. No sweat there. Not multiplied by anything, especially any power or derivative of y, so that's perfectly fine. However, this is nonlinear in y. It's squared in y, not linear in y. So it's a quadratic in y. Okay? Cannot be made to be linear. Perfect. Okay.
The one above that is.
What's that?
The one above that one is.
Yes, those are. Before you came in, this was an unusual one because it was written in that form. Now, ignore my lines here, okay? And maybe a little harder to see. So what we did was rewrite that by dividing everything by dx to get this in the derivative of y, and then you have y minus x, and this disappears as 1. Plus 4x times dy dx equals 0. Okay? Well, that's fine. And so I'll rearrange the order, put 4x dy dx here, plus y minus x here equals 0. Add x to both sides if you want to. 4x dy dx plus y equals x. That's linear because that's to the first power, that's to the first power. Perfectly fine. This, every one of those is to the first power. That's linear second order differential equation. And this one, that's a function of x alone, that's a function of x alone. This is not multiplied by anything to do with y. That's not multiplied by anything to do with y. That's not multiplied to do with anything to do with y. So this is linear on this side. It doesn't matter what e to the x is there. It doesn't have to. But this one was nonlinear because you had, in this term, when you distribute, y times y prime, that's no problem, y prime. But minus y times y prime, that then is a product of a function of y and a derivative of y, not linear. This would have been linear, that it doesn't matter. This is the one that threw that one. Okay? On this one, second order differential equation, but not multiplied by any y or derivative of y, so that term's okay, but that's not a linear in y. That's very curved in y. Okay, and same thing with this one. Fourth order differential equation, perfectly fine. Ordinary differential equation, perfectly fine. This is to the first power, so that's perfectly fine, but this y is to the second power, no longer linear. Okay. So those three were nonlinear. Okay. As was stated on page 2, one of the goals in this course is to solve or find solutions of differential equations. In the next definition, we consider the concept of a solution of an ordinary differential equation. So, seems like at least one of you don't have a book still, so let me write this down. The definition 1.1.2, the solution of an ordinary differential equation. Any function, I abbreviate like crazy, phi, defined on some interval I, and possessing, so I shouldn't have my comma here yet, and possessing at least n derivatives okay, abbreviating like crazy, that are continuous on I, which, when substituted into an nth order ordinary differential equation, that's pretty ugly substituted, into an nth order differential equation, I'm going to put DE for differential equation, reduces the equation to an identity Again, my writing getting awfully sloppy, is said to be a solution. Of that differential equation on that interval. The equation and the interval are important. Okay. Now, a lot of blah, blah, blah there. A function phi, defined on some interval I, possesses at least n derivatives that are also contained in that interval I, which, when substituted into an nth order differential equation, reduces that equation to an identity, then that's the solution. So in other words, if this function phi, when you do the things to it that it says to do, take derivatives of the same, put it all in there, and you get an identity, then it's the solution. Okay? A lot of blah, blah, blah for telling you what a solution is. In other words, a solution of an nth order differential equation is a function phi that possesses at least n derivatives for which, this is written in that other form, f of x, for some reason it's not writing, okay, there it is, f of x, phi of x, phi prime of x, phi double prime of x, keep going up to and including phi to the nth of x. That's the nth derivative of phi of x. Okay. That closes out the function thing. That's equal to 0. Okay. For all x's in that interval. Okay. Okay. Now, again, a lot of verbiage, but you see everything that was said here, it's defined on I, as there, possessing at least n derivatives, okay, that are all also continuous on I, and which was substituted into any nth-order differential equation, reduces that equation to infinity. That's said to be a solution. So this thing comes down to 0. You plug it all in and everything balances everything else out. That's said to be a solution. Now, we say then, and another way of doing, not only is it a solution, we say that phi satisfies the differential equation on I. Okay? We'll also assume that the solution phi is a real valued function. In our introductory discussion, we saw that, okay, here's that example we saw to the very beginning. Y is equal to e to the 0.1 x squared is a solution to this differential equation. dy dx, first order, is equal to 0.2 xy on the whole interval . Okay. All right. Occasionally, it will be convenient to denote the solution by an alternative symbol, y of x. Who cares what you call it, okay? Phi of x names it as a different function. The other way of saying it is sometimes y of x, okay? Let's still talk about the same function. They just use the symbol here to represent the function, okay? Not a different one. Now, you got this okay? Can I move on? Okay. We've been mentioning these intervals, okay? These are called the interval of definition. You cannot think solution of a differential equation without also simultaneously thinking what interval is that a solution on. Every solution has some interval. Now, it may be all real numbers, that's fine, okay, then everything. But some can only be defined in certain intervals, and we'll see that. The interval in that definition that I had on the previous slide, definition 1.1.2, is variously called the interval of definition, the interval of existence, or the interval of validity, or the domain of the solution. All those things can be referred to as the interval, okay? It can be an open interval from can be an open interval called A to B, a closed interval, bracket AB, or an indefinite integral, A to infinity, and so on. Okay. A lot of blah blah. Let's do example 5. Verify that the indicated function is a solution of the given differential equation. Now, hint, you're going to see this kind of thing on your test. There's not a lot of solving things in this first chapter. It's a lot of talking about things. So basically you got to, one thing they do a lot of is verification of solutions. They don't tell you how they got the solution. We'll do that in later chapters. They just will say, here's a solution, verify it. Okay? So that's exactly what example 5 is doing. Verify that the indicated function is a solution of the given differential equation on the interval negative infinity to infinity. So here is the differential equation. dy dx is equal to xy to the 1 dy dx is equal to xy to the 1/2. Okay? Y is equal, now this is what they're suggesting as the solution. 1/16 x to the 4th. Okay. Now they ask you to verify that that solution, that function, y is equal to 1/16 x to the 4th, is a solution of this differential equation, dy dx equal to xy to the 1/2. All right. There's two things you've got to do to the right to fit it into the left. What's one of them? Find a derivative for sure. So let's do that one. Y, let's call it dy dx is equal to what's dy dx? If that's your y, what's your dy dx? 1/4 x cubed. Perfect. So, this thing we're going to put over here. We've still got one other thing to get out of that y. What's that? The square root of y. Okay? So we got y. Let's now figure what the square root of y is. Anybody? One-fourth x what? Squared. Perfect. Okay? Now, let's plug and chug then. Let's put this in here, that in here. So this gives you 1/4 x cubed is equal to x times xy to the 1/2 is 1/4 x squared. Okay? Let's see what we got. 1/4 x cubed, left hand side, is equal to 1/4 x times x squared is x cubed. Okay? Yeah. That's it. Isn't it? Yeah. 1/4 x cubed is equal to 1/4 x cubed. An identity. So you now have verified that that differential equation, that the right-hand thing, y is equal to 1/6 x 4th, does solve that differential equation. Do you see? Does that make sense? Okay. That was the A part. Is it all right for me to erase the A part and get to the B part? Okay. Goodness gracious. A break between classes, I should have stopped and gotten a little bit of soda because, oh. What's that?
I said, I'm there with you.
Yeah. It's,
I went in at 5 this morning.
oh wow. Yeah, I woke up at 5:30 this morning, but that's not the same as going to work at 5. All right, y double prime, this is the b part of example 5, minus 2y prime plus y is equal to 0. There's your differential equation. This function is what we claim we want to verify if this is a solution or not. Y is equal to x e to the x. All right. Now, again, on this one, there's two things to get out of the right, so we can put them into the left. What are they? Okay, say again. Yeah, first and second derivatives. So let's do y prime is equal to, this is product rule. How does it go? X e to the x, is that what you said? Plus e to the x. Okay, I couldn't hear it. Okay, the first we got by the first times the root of the second. The second part there we got by the second times the root of the first. Yeah. Now, you said we need second derivative as well. Yep, we do. So y double prime is e to the x plus x e to the x plus e to the x. To simplify that a little bit, we combine these two together, and that gives you 2e to the x plus x e to the x. Now, you could say that's 2 plus x times e to the x. I don't think that's any easier. So let's leave it alone, just like we have it, and go back and plug in. So y double prime is 2e to the x plus x e to the x minus 2 times y prime, x e to the x plus e to the x, plus y is x e to the x. Goodness, that's ugly. X e to the x. Okay. Yeah. Okay. And the question is that equal to 0? Well, let's see. First thing we've got to do is distribute our minus 2. So this is going to be 2e to the x plus x e to the x minus 2x e to the x minus 2e to the x plus x e to the x. Is that equal to 0? All right. Now, here we have a 2e to the x and a minus 2e to the x. Those go to 0. Here we have an xe to the x, another xe to the x. That gives you 2xe to the x minus 2x to the x, 2xe to the x, and that gives you 0 as well. So yes, again, that gives you an identity. Now, that's what it means to verify that that is a solution to that. You do what is required to get it to look like the differential equation, then plug it in to those pieces and see if it gives you what it says. 0, e to the x, whatever the right-hand side is. All right. Now, it says here, note 2, that each differential equation in example 5 possesses the constant solution y is equal to 0 for any x that you happen to choose. Now, I've already erased the first one, but here's another one. If y is equal to 0, that's 0. Y prime is 0, so that's 0. And y double prime is 0, so that's 0. And 0 plus 0 plus 0 is equal to 0. That's an identity as well. So that is what we call the trivial solution. That is always true. That works when this is a I'm going to use the term on you here, homogeneous differential equation. In other words, it's equal to 0. The trivial solution will almost always be a solution to that differential equation. Okay. The only reason I say almost is you could finagle one around to get it so it wouldn't, but most of them it would. Okay. Note that for each differential equation in example 5 possesses a constant. Oh, I already said that. Now, let's go back to that interval concept. Okay? Now, think here I'm going to go to my graphing. I think I'll erase this. Can't get it to click. There it goes. Now, the graph of a solution phi of an ordinary differential equation is called a solution curve. Since phi is a differentiable function, it is continuous on its interval of definition, or one of those other words we used back there. Okay? Thus, there may be a difference between the graph of the function phi and the graph of the solution phi. Put another way, the domain of a function phi need not be the same as the interval I of a definition of the domain. All right, I'm going to sort of leave that alone. Here's example 6. Oh, that's what I was going to do. Yeah. Here's example 6. The domain of this function, y is equal to 1 over x. Can anyone tell me what the domain of that function is? Yeah, I know I heard the first part. Anything from negative infinity up to 0, but not counting 0. You can't divide by 0. And then anything to the right-hand side beyond 0, no matter how close you get, it's okay, to positive infinity. So those two pieces of your domain. Okay. So, already, I know something about an interval here. If this is a solution for a differential equation, this is only good from some minus number to some other minus number, but not 0, or from some positive number to any positive number as long as you don't include 0. The interval could not be from here to here, here to here, here to here, because x equals 0 cannot be in that. So you'd have to be some interval to the left or some interval to the right of your vertical asymptote. You cannot include the vertical asymptote. So this would graph to be something like this. Oops, I didn't quite get it right. Okay, something like that. Nothing to the right. I mean, any interval that does not contain x equals 0 to the right-hand side or the left-hand side can be those two intervals would be fine. You cannot have an interval that crosses the x-axis, the y-axis. All right. Now, the domain of this y is equal to 1 over x is considered simply as a function. Okay? It's a set of all real numbers except x equals 0. This is excluded because you cannot have a value in that. Okay? When we graph y is equal to 1 over x, we plot points on the xy plane. Yesterday, I forgot to bring my glasses, so everything I did was so tiring to my eyes. And today, even though I got my glasses, my eyes are still rebelling against yesterday. They're just almost stroking on me. That's a bit extreme, but anyway. We plot points in the xy plane corresponding to judicious sampling of numbers taken from its domain. The rational function y is equal to 1 over x is discontinuous at 0. Its graph in the neighborhood of the origin is given by this figure here. You can go back to 1.1.18. So anyway, it's that function right there, or something that looks sort of like it. The graph in a neighborhood of the okay, I think it's saying the same thing I did. You have anything here but x equals 0, you cannot. That cannot be in any interval for which it is. Now, that is a function, and that's how we graph the function. Now, the B part says y is equal to 1 over x. This is the function, and that's how we graph it. The solution, y is equal to 1 over x, okay, is a solution of a linear first-order differential equation, xy prime, plus y is equal to 0. Okay. Ugly x. Let me see. Oops, that's not what I wanted. Okay, that's better. Whew. That same expression, y is equal to 1 over x, if that's a solution of a linear first-order differential equation, say this one, xy prime plus y is equal to 0. Okay. All right, now they say verify. So let's go back and verify like we did before. One step do we need here? Take a derivative, okay? Now, I'm trying to figure out why I wrote that twice, so I'm not sure. Let me erase the second time. I think I was copying something over that they had, okay? So, before I take a derivative, I don't like to take it in that form. What's a better way to write the function before I take a derivative? X to the minus 1. Now take the derivative. Y prime is equal to negative x to the minus y, right? No, minus 2. Goodness gracious. I was looking at the wrong thing. Minus 1 times x to the minus 2. Okay, got it. Now, if you wanted to, you could go back and rewrite this as minus 1 over x squared. If you wanted to. No problem with that. So let's now plug that in for y prime. This will be x times a minus 1 over x squared plus y was 1 over x. Okay, I'm sorry, my pen slipped. I've got 2 more hours of teaching after this class. I don't know. I'm going to have to get a good swig of Coke before I go over there. Okay. Right. That's equal to 0. Is that true? Well, here, this x will cancel out one of those, and you have 1 minus 1 over x plus 1 over x, and sure enough, that's equal to 0. That does check. Now, you have now verified that is a solution. But when we say that y is equal to 1 over x as a solution to the differential equation, we mean that it is a function defined on some interval which is differentiable and satisfies the equation. In other words, y is equal to 1 over x is a solution of the differential equation on any interval that does not contain 0. And that's what I was saying before, like minus 3 to minus 1. Yeah, that would be perfectly fine. 1/2 to 10. That would be fine, as long as it doesn't include 0. Okay? You could even expand it as far as you could and have from negative infinity to 0, as long as you put parentheses around both. Negative infinity is not a number, so you need a parentheses there. 0 is a number, but that means you can't include 0. Or over here, 0 to infinity. Perfectly fine. Any of those intervals, that's a solution. But, says because the solution curve is defined by y is equal to 1 over x in any of those intervals, are simply segments or pieces of the solution curves defined for 0, negative infinity to 0, it makes sense to take the interval to be as large as possible. Thus, we take the I to be either this one or that one. Okay? No reason to have little pieces that you might want to expand. These will work. But you can't have anything that bridges 0. It just can't happen. Now, voice feels like it's about to go on me. Sorry about that. Let's go back to a clear slide. And the next subtopic here is explicit and implicit solutions. Okay? How are we doing on time? What's that? 20 minutes. Just asking to see if I think I can make it 20 minutes. Because, man, I've got 0 energy right now. Okay. When we talked about explicit or implicit solutions or functions, not solutions, functions, from calculus, a solution in which the dependent variable is expressed solely in terms of the independent variable and constants, that's said to be explicit solution. Okay? For our purposes, let us think of an explicit solution as an explicit formula. For instance, y is equal to some function of x and x alone. Depending only on expressions of the independent. Okay? We can manipulate those, evaluate, differentiate, do anything we want to using standard rules. Okay? These last 3 that we've done, y is equal to 1/16 x to the 4th, explicit. Okay? Y is equal to x e to the x, explicit, only equal in terms of x. The last one, y is equal to 1 over x. explicit in X. Okay? Now, for our purposes, let us think of the explicit solution as that. Okay, no, I'm sorry, we already did that. Okay. And these are, that we just did here, are explicit solutions of this. This one of dy dx is equal to xy to the 1/2. We've already shown that. The second one is of y double prime minus 2y prime plus y is equal to 0. That's, we know, was a solution. And the last one was x yeah, it came to, I was looking at the book and not at what I was writing, and they wrote too close together. Let me get this back. This one's a solution of x y prime plus y is equal to 0. Okay? Now, it says, moreover, the trivial solution, y is equal to 0, is an explicit solution for all three equations. So let's verify that. If y is equal to 0, its root of y is equal to 0. Doesn't matter what x is, it's a 0, and dy dx is 0. Okay? Here, demonstration that's ugly too. If y is equal to 0, y prime is equal to 0, y double prime is equal to 0. See, that works. If y is equal to 0, y prime is equal to 0, that's the equal sign there. So yeah, that all three of those do have the trivial solution. Okay? Goodness, this, one of the problems is the screen is wobbly, and when I'm writing, I'm not paying attention or holding it, it moves around on me. Okay. Now, when we get down to the business of actually solving some ordinary differential equations, you'll see that the methods of solution do not always lead directly to an explicit solution, y is equal to some phi of x. That's particularly true when we attempt to solve nonlinear first-order differential equations. Often we have to be content with a relation or expression that contains both x and y set equal to 0. So here is the definition. We've been talking about explicit. Here's implicit now. A relation g of xy is equal to 0 is said to be that's ugly. Okay. Is said to be an implicit solution I abbreviate like crazy of an ordinary differential equation ODE, ordinary differential equation, on an interval I, provided that there exists, can't write, at least one function phi, they love phi, that satisfies the relation as well as the differential equation. All right. Let's make that the differential equation on I. Okay. And when they say this, they mean it. It is beyond the scope of this course to investigate the conditions under which the relation g of xy equals 0 defines a differential equation function phi. So we're just going to leave that alone. Let's go on to example 7. I have to get some caffeine, I think. Here's a relation. X squared plus y squared is equal to 25. Now, why didn't they call that a function? Why did they call it a relation? What does that define? Is what? Yeah, what is that? Circle of radius 5. A circle of radius 5, is that a function? No, vertical line test fails in most places, other than plus 5 and minus 5, and anything beyond that never crosses. Okay, so it's a relation, perfectly good relation though. Okay, and that is an implicit solution of this differential equation. dy dx is equal to negative x over y. Okay? On the open interval, negative 5 to 5. Okay. Now, there is a reason that's an open interval rather than including the endpoints, negative 5 and 5. Okay? That's why it's parentheses there. Anyone know why that would be the case? Okay, why couldn't negative 5 and 5 be included in that interval? Because, now these are values for x, remember? Okay. When x is equal to negative 5, what's your y? 0. Y can't be 0. Okay. Yeah. And when x equals positive 5, y is 0, y can't be 0. Okay? So that's why you have to exclude those endpoints there. They're not endpoints, but the extreme points, minus 5 and 5. They have to be open dots there. Can't be on there. Okay. Now, what they say is, how do you go about verifying that that equation does solve this? Or that relation. It's not, well, it's an equation too. Equation or relation. Not a function though. Well, easiest way, I guess, to me it's the easiest way. You could solve for y, and then you have a piecewise defined function, and that would be y is equal to plus or minus the square root of 25 minus x squared. Well, that's awkward. But at implicit differentiation, do it. Differentiate that implicitly. 2x plus 2y dy dx is equal to 0. Okay, let's solve for dy dx. First thing we'd do would be subtract 2x from both sides. That would give us 2y dy dx is equal to minus 2x. Right? We want to solve that. Solve that for dy dx. That means you divide by 2y. Okay? Now this all goes out here, and this leaves you dy dx is equal to, that goes away, minus x over y. There's your differential equation. right there. But it's only defined from -5 to 5. Can't be to the left of -5 because there aren't any values that'll work. It can be any value between -5 and 5, but not -5 and 5. Nothing to the right because it's outside the circle. Okay. So when I make my circles, I'm not quite touching on those edges. Okay, that's the circle, that's the circle. Open.
Really close.
What's that?
I said it comes really close.
Yeah, exactly. Infinitesimally close. Okay. Now, and then they say the same thing I did. You could have done this the other way. Y squared is equal to 25 minus x squared, then do y is equal to plus or minus the square root of 25 minus x squared, and then plotted each of those. The plus one is the top half circle, the bottom is the bottom half circle. Now, there's nothing here that would seem to indicate you have to exclude plus or minus 5 from your domain, because this is okay. It's just that differential equation that requires you to exclude it. All right. Now I've been holding up my hands. Here's the actual picture. Here is the implicit solution, as long as you put an open circle there and there, which they didn't, or the explicit solution, y as a function of this, is either that half or this half. It can't be at the same time. So all depends on what the y value is. Now, because the distinction between explicit solution and implicit solution should be intuitively clear, which they love saying, we will not belabor the issue by always saying, here is the explicit or implicit solution. Now, again, this is mostly nomenclature, and it's such a pain in the neck. The study of differential equations is similar to that of integral calculus. When evaluating antiderivative or indefinite integral in calculus, we use a single constant of integration. Analogously, we shall see that in Chapter 2, in solving a first-order differential equation, we usually obtain a solution containing a single constant or parameter c. Okay? Solution of f of x, y prime equals 0, containing a constant c, is given in the set of solutions g of x, y, and c is equal to 0. Okay. Containing c in a given set of solutions, g of x, y, c is equal. Okay. That's called a one-parameter family of solutions. And solving an nth order differential equation, rather than first order, nth order, then you're going to come up with okay. Then you come up with an n-parameter family of solutions. You have g of x, y, and then c1, c2, c3, up to cn. That means that a single differential equation can possess an infinite number of solutions corresponding to an unlimited choices for the parameters. The solution of a differential equation that was free of parameters is called a particular solution. Now we're going to be hitting those terms more later, but you'll see that some equations you're going to have to introduce either one or more constants. Other equations don't have any constants. Those are called particular solutions. They don't get into the mix of the others. Now, what does all that mean? Well, let's see if, I don't know, no, we need example 8 to do that. Okay. Here's one example, going back to the one we just, similar to what we just did. In fact, I think I'll erase this so it won't be confusing. Okay. What if we have a relation like this? X squared plus y squared is equal to c. Okay? Last time it was 25, and we knew that was going to be a circle 5. Now, what could c be in this case? We're not going to limit it to one number like 25. What values could it take on? Any what? Any what? Any positive number. C couldn't be negative, could it? Can't possibly be, because you can't x squared plus y squared equal a negative number. It's always going to be positive. So to have a minus c in there makes absolutely no sense whatsoever. But any positive number c should work for you. Now 0 won't really work either, because then the only thing would be the trivial solution, x equals 0, y is equal to 0. Only way that could happen. Okay. So let's do example 8. And this goes back to the concept of particular solution, which doesn't mean it has any parameter required. So for all real numbers c, the one parameter family y is equal to cx minus x cosine x is an explicit solution goodness gracious. Okay. What do we mean by explicit solution? Y, single variable y, equal to all functions of x. No y's over here at all. That's explicit. Okay, what we're talking about before. Okay, is an explicit solution of this linear first order equation. X, y prime minus y equal x squared sine x. Okay? On the interval minus infinity to infinity. All real numbers. Says verify. Let's verify. What are we going to have to do that equation up here? Take a derivative. Y prime is equal to C, that's yes in Spanish, minus, second, cosine x plus x times sine x. Okay, let's see if we get the derivative. Yeah, did it right. Okay. Now we need to plug this in and see if we do indeed get an identity. So x times this y prime, which will be c minus cosine x plus x sine x, minus y, y is cx minus x cosine x. That should be equal to, we're asking ourselves that it is, x squared sine x. Okay? Well, let's see. X times c would be cx minus x cosine x plus x squared sine x minus cx minus x cosine x okay, is that equal to x squared sine x? Well, here's a cx and a minus cx. Here's, whoa! I know, I'm trying to find where I made my error here. Y prime, right there.
Because it's negative x cosine x, and the difference of the equation is negative y. So y distributed to c is.
Ah, there it is, yeah. That should be in parentheses there. And that would make that a plus. Now, that adds to 0, and this equals that. Sure enough, that's correct. Now, here's the catch to this. Even though the C is in there, C doesn't wind up here anywhere, okay? So, C can be any value in the world. It's not a fixed value C. It's whatever C it is. You know, it could be a 0, it could be a 17, it could be minus 4/3 pi. I mean, it could be anything. The equation doesn't depend on the value for C. Okay. Now, here is the system of equations of some of the solutions. The pink solution is when C is positive. The blue solution is when C is 0. The green is when C is negative. The yellow is probably also negative between C equals 0 and some larger negative number. So that is your family of solutions for various C's. Okay. Now, the B part here is this one. I think we're going to have to erase. Okay. Have we gone over? Wait, y'all aren't supposed to let me go over. That's especially not on Wednesdays. Because Wednesday I got to go to the other campus. So what we're going to do here, have we gone over? I think we have, haven't we? Okay. So next time we'll start with 8B. We got 8A done, but we didn't get 8B. So let me put this in its place. And we just got a little more to do to finish section 1.1. I think you could do any of the odds 1 through 7. The answers to the odd number exercises are in the back. So do any of them that have the answers in the back that you want to. Do number 9. Either 11 or 13. That's explicit or implicit. 15 or 17, you can do those. And you might be able to do 19. I think you can. And then 21 and 23 are basically dealing with what we were just talking about. And okay, I think we'll stop there and pick up the rest of those next time. Sure. And you're only going through 23. You need the back of the book too?
Yeah.
Okay, let me see if I can find those quickly. 1.1, yeah.
Got it.
Okay. All right. Good deal. Now,